Welcome to the Science Podcast. This is our very first deep dive, and we're going to be tackling a topic that's been generating a lot of buzz lately. Google's Majorana One. You've sent over a stack of articles and research on it, so let's try to break down what's really important about Google's claim of creating their first quantum computer chip.
It's certainly a bold statement. What makes this different from, the typical incremental tech advancements is Google's positioning of this as a fundamental shift, like the invention of the transistor.
Right? And the potential applications mentioned in these articles are mind-boggling, revolutionizing medicine, creating entirely new materials, maybe even cracking problems that would take the world's computers like billions of years to solve.
It's crucial to understand why quantum computing is so difficult before we dive into those applications. The problem lies with qubits, the building blocks of these computers. They're incredibly susceptible to errors, which makes scaling them up a massive challenge.
So building a reliable large-scale quantum computer is a bit like trying to build a house of cards in a windstorm.
A very apt analogy. Just as the transistor revolutionized classical computing, quantum computing needs a similarly groundbreaking technology to overcome these limitations, and that's where the Majorana particle enters the picture.
This particle is its own antiparticle, which is a concept I'm still wrapping my head around.
It's a unique state of matter, existing in a theorized topological state. Google claims to have not only observed but also controlled the Majorana particle, allowing them to create a new material they're calling a topoconductor.
Okay, so instead of directly using these incredibly sensitive qubits, Google created a new material to kind of harness them. What exactly is a topoconductor and how does it help?
Think of it as a hybrid, combining the robustness of a semiconductor with the special properties of a superconductor. This allows Google to create what they call topological qubits, which they claim are far more stable and less error-prone.
And these topological qubits are the key to building a truly powerful and practical quantum computer.
That's the idea. Now let's get to the heart of it. The Majorana One chip itself, it's designed with atomic precision, meaning Google can pack an astounding number of qubits onto a relatively small chip.
These sources mention a figure of over 1 million qubits, which is just wow. Can you tell me more about the chip's architecture and how it utilizes those Majorana particles?
Instead of electrons, Google is using Majorana particles for computation, representing a radical departure from conventional approaches. The Majorana One chip functions as a quantum accelerator, working in conjunction with a classical computer. This setup enables researchers to perform incredibly complex simulations in fields like chemistry and material science.
So are we talking about a complete replacement of classical computers, or is it more of a collaborative effort?
For now, it's more about collaboration. The quantum accelerator tackles the complex calculations, while the classical computer manages the overall system. This allows us to start exploring practical applications sooner rather than later.
Speaking of applications, let's talk about the potential impact of having a 1 million qubit quantum computer at our disposal. These sources suggest everything from revolutionizing medicine to creating entirely new materials with unheard of properties. Where do we even begin?
The potential applications are vast. Let's start with medicine. Imagine using Majorana One to simulate the complex interactions of molecules in the human body. This could lead to the development of highly targeted drugs with minimal side effects personalized to your specific genetic makeup.
So we're talking about a future where drug development is not only faster but also incredibly precise, leading to more effective treatments for a wider range of diseases.
Exactly. But the possibilities extend far beyond medicine. Imagine using Majorana One to simulate the properties of materials at the atomic level. We could potentially design materials that are lighter yet stronger than anything we have today, revolutionizing industries from aerospace to construction.
It's like opening a Pandora's box of possibilities for material science. One of these articles even suggests that Majorana One could help us create materials with completely new properties, things we haven't even conceived of yet.
It's certainly within the realm of possibility, and that's just scratching the surface. Majorana One could have a significant impact on fields like energy production, climate modeling, and even artificial intelligence, potentially leading to solutions for some of humanity's most pressing challenges.
It's clear that the potential impact of a 1 million qubit quantum computer is enormous. But some of these sources also raise concerns about the challenges involved in actually realizing this potential. Google's claims are bold, and they haven't exactly shied away from painting a very optimistic picture. What are some of the hurdles they need to overcome to truly deliver on their promises?
Scaling up production is a major challenge. Building a single chip is one thing, but manufacturing millions of these chips with the required atomic precision is a monumental task. Ensuring the stability and reliability of those 1 million qubits over time is another hurdle.
So it's not just about building the chip, it's about making sure it can function reliably and at scale for practical applications. What about the software needed to harness the power of Majorana One? Is that keeping pace with the hardware development?
That's another critical aspect. Google has been developing a quantum software platform called Cirque. But as the hardware evolves, the software needs to keep up. Developing algorithms that can effectively utilize the power of a million-qubit computer is uncharted territory, and it will require significant innovation.
So it seems there's a lot of work ahead for Google, both in terms of the hardware and the software. But what sets their approach apart from other efforts in quantum computing? Why are they so confident in the Majorana One chip?
One key difference is their use of topological qubits, which are inherently more stable and less error-prone than other types of qubits. This, they believe, is crucial for building a quantum computer that can be scaled up to millions of qubits and operate reliably.
Their bet is that these topological qubits are the key to unlocking the true potential of quantum computing.
That's their claim, and the results they've shared so far, while preliminary, are certainly intriguing. They've demonstrated control over these qubits with remarkable precision, which is a significant step forward. But the road to a million-qubit quantum computer is long and challenging.
It's a fascinating story unfolding, and I'm eager to delve deeper. However, before we get ahead of ourselves, let's pause here and allow our listeners a moment to digest all this information.
We've been discussing the potential and challenges of Google's Majorana One. It's exciting stuff, but let's not forget that this technology is still in its infancy.
Right, we're not talking about quantum-powered smartphones hitting the market next week. So what's next for Google? What are the next steps in their quantum journey?
Scaling up production is a critical hurdle. Building one chip with a million qubits is a remarkable achievement, but to make a real impact, they need to produce these chips reliably and on a large scale.
That sounds like a manufacturing challenge of epic proportions.
It's a complex undertaking, to say the least. Refining their atomic precision techniques and overcoming various engineering hurdles to ensure each chip performs as expected will be crucial.
And let's not forget the software side of the equation. A million-qubit quantum computer needs the right software to unlock its power. What's the status of software development for Majorana One?
That's a crucial point. Google's Cirque platform allows developers to create algorithms specifically designed for quantum computers, but software must evolve alongside the hardware.
So it's a two-way street. The hardware needs advanced software, and the software needs powerful hardware to truly flourish.
Absolutely. It's a symbiotic relationship. Both sides need to advance in tandem for quantum computing to reach its full potential.
We've established that powerful quantum computers are on the horizon, but there's still a lot of work to be done. It all sounds incredibly complex.
It is complex, but that's what makes it so fascinating. We're venturing into uncharted territory, pushing the boundaries of technology. And with complexity comes the potential for unexpected discoveries and breakthroughs.
What are some of the specific challenges researchers face when working with these quantum computers?
Well, quantum computers are incredibly sensitive to their environment. Even the slightest vibration or temperature fluctuation can disrupt those delicate quantum states and lead to errors.
So it's not just about building the hardware. It's about creating a perfectly controlled environment for these machines to operate.
Precisely, Google has invested heavily in specialized facilities that shield their quantum computers from any external interference.
Talk about high maintenance, but I suppose that's the price of working at the cutting edge of technology.
Indeed. And then there's the challenge of quantum entanglement, a phenomenon that's even stranger than it sounds.
All right, let's talk about entanglement. It's one of those concepts that captures the imagination, even if understanding it fully is a challenge.
It's this bizarre phenomenon where two particles become linked no matter how far apart they are. Whatever happens to one particle instantly affects the other.
It sounds like science fiction, but it's a real phenomenon that plays a crucial role in quantum computing, right?
Absolutely. Entanglement is the secret sauce that gives quantum computers their immense power. By entangling qubits, we can create complex, interconnected states that allow for calculations far beyond the reach of classical computers.
So it's like harnessing this spooky action at a distance to perform complex calculations.
That's a good way to put it. It's a concept that challenges our classical intuition, forcing us to rethink our understanding of reality.
Let's bring this back down to earth for a moment. How will all of this affect our everyday lives?
It's hard to say with certainty as we're still in the early stages, but imagine a world with faster drug discovery, more efficient energy production, and materials with properties we can only dream of today.
Okay, now you're speaking my language. Can you give me some concrete examples of how Majorana One could change things, starting with medicine? How will quantum computers revolutionize healthcare?
One of the most promising applications is drug discovery. Imagine using Majorana One to simulate the behavior of molecules with incredible accuracy. This would allow scientists to design new drugs and therapies much faster and more effectively than traditional methods.
So instead of taking years and billions of dollars to develop a new drug, we could potentially do it in a fraction of the time and at a fraction of the cost.
That's the hope. Quantum simulations could also help us understand complex biological processes leading to breakthroughs in a personalized medicine and genetic engineering.
What about materials science? The possibility of new materials with unique properties is particularly intriguing.
That's another area where quantum computers could have a massive impact. Imagine materials that are lighter and stronger than anything we have today, or materials that can conduct electricity with zero resistance.
Zero resistance. That means no more energy loss in our electronics. Sign me up.
It's certainly a tantalizing possibility, and there's potential for entirely new materials with properties we haven't even conceived of yet.
It's like opening a treasure chest of scientific possibilities. But I have to ask, are there any potential downsides to this quantum revolution?
That's an important question. Like any powerful technology, quantum computing has the potential for both good and bad. One concern is the impact on cybersecurity.
Right, I've heard that quantum computers could crack the encryption we use to protect our online data.
That's a real threat. The algorithms that protect our online transactions and communications rely on the fact that classical computers can't factor large numbers quickly. But quantum computers could potentially do this in a matter of seconds, making our current encryption methods obsolete.
So it's like giving hackers a master key to all our digital secrets. That's a bit unsettling.
It's a serious concern, but researchers are actively working on developing new encryption methods resistant to quantum attacks. The goal is to stay one step ahead.
That's reassuring. It sounds like a constant race between those developing encryption and those trying to break it with quantum computers as the ultimate weapon.
In a way, yes, but it's important to remember that technology itself is neutral. It's how we use it that determines whether it's a force for good or evil.
That's a good point. It all comes down to human choices and responsibilities. What about the ethical implications of this technology?
That's a crucial conversation to have. As with any powerful tool, we need to consider the ethical implications of its use. We need to think about who has access to this technology and how we can prevent its use for harmful purposes.
It sounds like we're standing at a crossroads and we need to choose the right path forward.
It's a lot to consider, but it's a conversation we need to have. The future of quantum computing is in our hands, and it's our responsibility to ensure that it benefits all humankind.
This deep dive has been quite a journey. We've covered a lot of ground, from the intricacies of qubits to the mind-boggling concept of quantum entanglement, all the way to the potential impact of this technology on our lives. Before we move on to the final part, let's take a moment to reflect on everything we've learned so far. We've explored the potential and the challenges of Google's Majorana One, and it's clear that this is a technology with far-reaching implications. But let's step back for a moment and consider the bigger picture. What does the emergence of quantum computing mean for humanity as a whole?
It's a question worth pondering. We often get caught up in the technical details, but the truth is this technology could fundamentally change how we approach problem solving, how we understand the universe, and even how we see ourselves as humans.
That's a profound statement. Can you elaborate on what you mean by changing how we see ourselves as humans?
Well, consider the potential of quantum computers to simulate the human brain. This could lead to breakthroughs in artificial intelligence so advanced that we might one day create machines that think and feel like humans.
That's both fascinating and a little unsettling. It raises a whole host of ethical questions.
Indeed, what does it mean to be human in a world where machines can potentially rival our intelligence and even our emotions? These are questions we need to grapple with as quantum computing progresses.
It's a lot to process, but these conversations are crucial. So what can we as individuals do to prepare for this quantum future? It all seems so complex and daunting.
The first step is to stay informed, learn about quantum computing, engage in discussions about its implications, and consider the ethical and societal aspects of this rapidly evolving technology.
Knowledge is power, as they say. And that's part of what we're trying to do with this deep dive, make this complex topic accessible and engaging. What else can we do to ensure that this technology is used responsibly and for the benefit of humanity?
We can advocate for continued investment in quantum research and education. This field needs support to flourish and reach its full potential, which could include solutions to some of humanity's most pressing challenges.
So it's not just about the scientists and engineers, it's about society as a whole embracing this technology and shaping its development in a positive direction.
Exactly. The quantum future is a collective endeavor. We all have a role to play in shaping it. Now, Google claims that Majorana One is a real breakthrough. What sets it apart from other efforts in quantum computing, and why are they so confident in their approach?
They've certainly generated a lot of excitement with their announcement. What makes Majorana One stand out?
Their approach centers on topological qubits, which they believe are the key to building a truly scalable and reliable quantum computer. These qubits are inherently more stable and less prone to errors than other types of qubits, crucial for reaching that million qubit milestone and beyond.
So they're betting on the inherent stability of this topological qubits to overcome many of the challenges we discussed earlier.
That's their claim, and the initial results, though preliminary, are promising. They've demonstrated impressive control over these qubits. However, it's important to remember that the road to a practical large-scale quantum computer is still long and full of challenges.
It's been an incredible journey exploring the world of Majorana One and the potential of quantum computing. To wrap things up, what's the one key takeaway you want our listeners to remember?
I think the most important takeaway is that we're witnessing the birth of a technological revolution with the potential to reshape our world in profound ways. It's a revolution that will touch every aspect of our lives, from medicine and materials science to energy and artificial intelligence.
It's a future full of potential, but also one that requires careful consideration and responsible development.
Absolutely. We need to be mindful of both the benefits and the risks, working collectively to ensure that this technology ultimately serves the betterment of humanity.
This deep dive has been incredibly insightful. Thank you for sharing your expertise and helping us navigate this complex and exciting topic.
It's been my pleasure, and thank you to our listeners for joining us on this journey of discovery. If Majorana One delivers on its promise, which field do you think will be most transformed? We'd love to hear your thoughts. And be sure to subscribe to the Science Podcast for more deep dives into the most fascinating scientific breakthroughs of our time. Until next time, keep exploring.